Okay, so we are going to, stop with this. This will be the last lecture on the PDPA series. And if you recall that in the last lecture, we essentially talked about that how the two laser beams as they intersect, and then you capture the signal from two detectors which have the same scattering, order, but they are coming from two different beams. And we talked about that the frequency actually measures the velocity, whereas the phase shift measures what will be the particle size. And this came out of this particular equation. If I just move back a little bit on here. So this was the expression, and there was a 2 pi bias that we talked about, and that bias was taken care of by using a third detector. So the third detector was used. Let me find that slide once again. Third detector was used to find the 2 pi bias, okay, to relieve of the 2 pi bias essentially. So this was what was done with the third detector. Okay, so this is the standard system, and then we talked about that there could be a planar system which has got zero elevation, and then we got the, we can do actually what we call a sphericity validation. So a lot of things like that could be done using this. And then you can also have, this is from Nicholas Appel's thesis, that all the points which are away from this line we kind of reject, and then whatever is in this band we accept. That is the spherical validation from the dual mode. Dual mode is basically standard and plane. So that is how these things is done. One is along the meridional circumference, and one is along the equatorial circumference. Okay, so that is how this was done. And then the exchangeable spatial filters and whatnot. Okay, so ultimately we talked about the data processing, what is a coherence part and what is a quadrature part. And when the signals are in phase, they all fall into the coherence bucket. If they are not completely out of phase, they go into the quadrature bucket. So basically the angle between these two, the argument arctan, is basically, or the argument of the cross spectral density function gives you the phase, and that is what is used to extract the phase difference, and hence the droplet or the particle diameter in this case. So this is how these things are going to pan out. All right. So let us look at now some of the examples, and this is once again from Nicholas Appel's thesis. This is a project in which I was also involved quite actively, because this was a part of an Indo-German Science and Technology Center project on closed coupled atomization, and we did the shock droplet interaction, whereas Nicholas Appel did the the closed couple, the full scale closed couple atomizer operated with water and air. So this was supposed to be operated with liquid metal. Okay, so that is how they actually create this metal powder, so to say. So this has got varieties of parts. The video is not going to play, but I can take you through that. There are the characteristics of such an atomizer is that it has got very high liquid mass flow rates, about 9 kg, about 3 kg to about 9 kg per minute. It has got a strong two-way coupling. Two-way coupling means where the flow actually, where the liquid actually influences the airflow, airflow influences the liquid flow, and stuff like that. Then if you look at the different locations which are marked as 1, 2, 3, 4. For example, 4 is a region of very high local gas velocities. It's about 660 meter per second. And 3 is a region of highly expanded gas nozzle. So these are the different features. So the experimental challenges were many. It had short time scales, it had wide range of length scales, and it is a very dense spray at the same time. And there is a lot of feedback that goes on. The structures are very turbulent and things like that. So the equivalent of that, even shorter time scales, were the shock droplet interaction, which we did at IISc, and some of those videos we will play in a subsequent at a subsequent time. But essentially what that also shows that the time scale can be very short, even much shorter than this, and it is a challenge therefore to measure the droplet sizes and velocities in essence. So what was done was that Professor Tropia's group used a dual mode phase Doppler configuration. So they had a standard system and they had a planar system, and the assessment sphericity was that D should be less than 107 micrometer, and it's a 3-axis traverse. So what happens is that this is the transmitters, these are the receivers, and then you have the velocity. So these are exemplary, measurement locations along the z-axis. This is how it comes out of the atomizer. So the average validation and spherical validations rates were about 75 and 70%, which is because you tend to get a lot of ligaments and flattened discs and oblate type of droplets in such configurations, as you can see. And so 75 and 70%, honestly speaking, is pretty reasonable to begin with. Okay, and the measurement location, if you look at it, it is like 500 mm downstream, and you can go radially from 0 to 100 mm, assuming that the spray has a radial symmetry. Not always the case, but in this case, with that assumption, you can get some example measurements in such a setup, which is this is a setup where measurement was really tough. That's why it is being shown over here. And using the PTPA in shock, you cannot use it at all. So there we will use something called the depth from defocus technique, which we'll cover in a later lecture. Okay. So the size distributions, which is number versus volume weighted. For example, this is the PDF. This is the particle diameter, and this actually shows the number weighted, and this shows the volume weighted. So you can see that how the diameter actually, when you have number weighted, the diameter is like the peak diameter falls under 25 micron, more like in the band of 15 to 20. Whereas if you do volume averaged, it is always weighted towards the larger droplet size scale. As a result of that, you have this diameter around, say, 25 to 30. Okay, so these are the kind of size distribution measurements that you get. Different droplet diameters, you sample it, and then you do whatever statistics that you want. So in this case, you can do number weighted average, or you can do volume weighted average. So all these things can be done in these kind of, so any type of statistics. The idea is to show that any type of statistics can be generated. And why they are useful? Because it tells you that how the nozzle is functioning. What is the functional characteristics of these nozzles? And that is very important, because you need to know how the nozzle actually behaves. Okay, and whether it is good for closed couple atomization, because it is used for metal powder production, for example. So this determines what will be the powder size, for example. Okay, because these droplets are going to shrink, they are going to solidify and form this metal powder. So this size distribution has a direct correlation with the powder. So that is very important, and that is what this particular measurements will actually show. And then, of course, you can also vary the gas stagnation pressure, and by varying the gas stagnation pressure, this is along this and this is along that. So you can actually measure the number of median diameter droplets. So that is what you see, that with increase in stagnation pressure, this comes down. Okay, so you can vary the liquid flow rate, you can vary the stagnation pressure, and that is what is done. The liquid flow rate is varied over here and over here. So you can vary multi-parameters and try to find out that what is the number median diameter, which is called EN15, that we can get in these kind of measurements. Okay, so it gives you the statistics, which is very important for actually optimizing the performance and even to characterize the performance. So this is also the liquid mass flow rate variation has been studied in details, and this is again the number median diameter, So the liquid mass flow rate has a strong influence on particle size and its dispersion. So this also enables us to see that what functions or what parametric space one can play with to control the droplet diameter size. And this is only possible because you can use PDPA to measure the droplet diameter. So that becomes a mission critical part of this particular measurement technique, so to say. And this is very, very important. Okay, and so this is one example. And of course, you can also vary what we call the gas to liquid ratio. So it is often touted as m dot g by m dot l, and you can once again plot the diameter or the median diameter of the droplet in microns for different GLR values. For low GLR means that the liquid mass flow rate is actually larger compared to the gas mass flow rate, and not larger with respect to the gas mass flow rate. Sorry, the gas mass flow rate is always larger, but the liquid mass flow rate is lower. So you can hold the gas mass flow rate constant, and you can go on decreasing the liquid mass flow rate, or you can increase the gas mass flow rate, keeping the liquid mass flow rate constant. Okay, either way, this is perfectly feasible. And then it is the gas to liquid GLR on its own is not suited to, for example, this showcase that it is not suited for describing the atomization results. So this can also be used for even more in-depth fundamental studies, like how the atomization actually happens, what are the atomization modes, and one can actually conceive of empirical models on this. So there is a lot of things that you can do in a complicated setup like this, okay, which is high speed, and using a dual mode PDPA technique by measuring it across multiple sections, and doing it at very reasonable accuracy of 75 and 70%. So that is a great thing, so that we can get measurements under very harsh conditions, so to say. So these are the empirical models that you see. So now that we have covered all these things, now let's do a very quick runaround of interferometric particle imaging. Okay, so now that we know phase Doppler, we know LDV, and we know scattering, and we know a lot of stuff, the interferometric particle imaging technique is something that is will not be alien anymore. If you look at, again, go back to this particular picture where you have this particle or a droplet, and then you have an illumination source, and then you have a receiver which monitors some scattering order. Now, if you look at this large particle or this particular drop, whatever it is, this is the first incident point of first order refraction, and this is the first glare point of first order refraction. And this is basically the incident and the glare point of the reflection. So these are two different scattering modes. Okay. However, so these will both give rise to two glare points. So how about we monitor this, which are across two different scattering modes, remember, and try to get an idea of what will be the diameter of the droplet. So the path from the incident wave to the detector is unique for each scattering mode. The large particle images, incident point onto the detector through the glare points. So both these points are unique for each scattering order or the scattering mode. And these are, so assuming that these are coherent, okay, and both of them lie on the same scattering plane. So they are at the same scattering plane, but they are different scattering modes or different scattering orders, and they are coherent to begin with. So you understand the difference. So this is first order refraction, this is reflection. So they are two different scattering mode or order, but they are coherent and they lie on the same scattering plane, okay? And when they are illuminated in a particular direction, and these paths are very unique, and so you get basically two glare points from two different scattering modes. How this can be used, that is the main purpose. So let's look at this, where we say that this is, for example, a laser. Now this is expanded into a sheet. Okay, so this is a laser which is expanded into a sheet, and then there is a particle. Okay, so this particle, what will happen if you look at it? So this will be kind of the reflection, and this is the first order refraction. The lower part is the first order refraction, the upper part is the first order reflection. Okay, so what happens? So they will give rise to two glare points. Again, they are at the same scattering angle. Say that is what we are monitoring it with. Okay, so and this is usually at 90 degrees. Okay, so what happens is that then you have an aperture, and then you have the lens. Okay, the aperture cuts off a part of the beam, that means keeps the measurement region in check. And then if you use an imaging optics, normally you can focus it tightly, and you will get these two very focused glare points. So these glare points are nothing which are coming from this point and this point, again on the meridional plane, but they are from two different scattering orders. Remember? So this is the point at which these two images are very tightly focused. Now what you do is that this is very hard. This is looking at one particular particle and focusing it like that. Now what you can do is that you now kind of move the plane either this way on the right hand side or on the left hand side intentionally, which is away from the focal plane, so it is not tightly focused anymore. So what do you expect? You expect the images to get blurry. Okay, and as you move it more, the images start to interfere with each other. The two modes starts to interfere with each other, and if you move it further, you will get a full fringes because of the interference of the two scattering modes. So these are basically the defocused images, and these are basically the scattering. These are the fringe patterns that you form because of the interference of the two different modes. Now, if you now know the fringe spacing, okay, and if you can image that, you can find out what will be the particle size, because they are coming from two distinct glare points from the particle, okay, from each particle, correct? So what you see over here are, you see all these things and you see the fringes, right? You see those fringes, right? So these round colored things that you see, or this round basically, these are not particle size. These are nothing to do with particles. This is basically the image of your lens. If the lens is square, this will be a square thing. Okay, so this has nothing to do, this particular profile, this particular image that you see has nothing to do with the particle or the droplet size. What the information that is inside these spots, or inside these spots that you see over here strewn all over, okay, are the fringes, and these fringes or the fringe spacings actually gives you an idea that what is the particle size or what will be the droplet size. So in other words, here you're using a single laser. A single laser is expanded into a beam. This beam actually forms a sheet, and then the particles are in that sheet going in or out. Okay, as it happens, what happens is that the particles will actually, or the droplets will actually have the reflection and the first order refraction, two glare points. You can focus the glare points into two distinct glare points also, and this will also enable you to measure the droplet size, by the way. But intentionally, for the ease of comfort, you move them so that these two scattering orders starts to interfere with each other. As a result of that, you get this fringe spacings, or these fringes, and by looking at the distance between the fringes, you can extract what will be the particle size. So, and one thing you remember, these sizes, these spots that you see are not the droplet sizes, but what is contained inside it, the fringes, that is what gives you the droplet sizes. All right. So this is basically called interferometric particle imaging, or IPI, so to say. Okay. This was also done by Professor Tropia for Dantec dynamics. Okay, so you can actually improve the particle image recognition by using two detectors. One is in focus, and the other, this one is in focus, the other one is in out of focus. So you can kind of locate the locations of the particles and then get the size. That is also possible to do by these kind of measurements. Okay, so this is kind of acts as like where the particles are to begin with, because sometimes you may not be in a good position to see that where all those particles are. I mean, okay, so the image shape is given by the aperture shape. that is the image shape that you see over here. Okay? That's the aperture shape. The particle image size is given by the degree of out of focus. The particle size is given by the fringe frequency or the number of fringes. Okay, so that is once you know the fringes and the spacing between the fringes, you can calculate the particle size. So this is very important. This is what IPI actually does. Now you can go one level further and you can use high-speed cameras now. So once you use high-speed cameras, the IPI technique can be combined with PIV technique for providing both size and velocity of droplets in an illuminated plane. So how does it do it? It captured the first image, then determination of the defocused image sizes and position. Then you capture the second image, determination of sizes and positions for the second illumination, and comparison of the two illumination and the determination of the particle velocities. So since these days high-speed cameras, everybody has got high-speed cameras. So the IPI technique can be routinely combined with high-speed cameras, to also give particle velocities as well as the size information. Okay, so in this case, remember we are using one laser only. Okay, but the idea is to have them interfere with each other so that we know the fringe spacing and the fringe frequencies from which the particle sizes can be extracted out. So in summary, the phase Doppler technique is the interference of scattered waves of the same scattering order. Remember, you are doing first order refraction with first order refraction, but this is the interference of scattered waves from two incident waves. There are two incident waves which are getting interfered. Okay, so two incident waves are getting scattered by this particle, and those waves actually interfere, but they are of the same scattering order, which means that they are coming from either first order refraction or reflection or whatever. Interferometric particle imaging is the interference of scattered waves from the same incident wave, not two, because you need only one laser, but they are of different scattering orders. That means you are watching the scattering order from refraction, first order refraction with reflection, for example. It's not first order refraction with first order refraction, it is first order refraction with reflection. So that is the difference between the two. In one case, you require two lasers, need to form a spot size and stuff like that, but it is the same scattering order, but it is coming from two different beams. Okay, but here it is coming from a single incident wave, but it is of different scattering orders. Okay, this is done during simple imaging using a camera, and this can also use a laser sheet. This is like a measurement volume, what we talked about, like the cigar-shaped measurement volume that we used routinely for LDV. Okay, so phase Doppler technique is a counting technique which offers high accuracy for velocity and size measurement for spherical particles. Sphericity determination is an important parameter which we talked about earlier. For reliable measurements, one scattering order must be dominant on the detectors. That's why you have to look at the scattering angles and for the relative refractive index and determine which one you are going to use, and accordingly park your laser and your receiving optics. The dual mode configuration allows this spherical validation, which is a very important part because spherical validation is what we need for doing these kind of measurements. Because the non-spherical particles are routinely rejected. There was also, by using 3 detector assembly, you could actually remove the 2 pi ambiguity. The planar size measurements, because it's on a sheet, are possible using the interferometric particle image technique, just by counting the interference fringes and the spacing between them. That is what is called IPI is all about. Okay, but the techniques are kind of similar in many ways, but there are differences because both are interference-based techniques, both phase Doppler as well as interferometric particle imaging. All right. So there are a lot of literature that one can go through. Okay, there is a tons of literature. Okay, on this. Feel free to look at all the literature and more. Okay. And this comes from the Professor Tropy, as I said before the start of this lecture series, is one of the pioneers of this PDCA technique, and these lecture notes are courtesy of him. Okay, So there are, of course, more details, more analysis, more things that can be learned from these particular, this particular mode of measurement. We have covered just a few, and of course we will try to give a lab demonstration also of the same. But I think more or less you get an idea that how the techniques actually work and how is it tightly linked with the optics. So the optics lectures were very useful, I would say, for both LDV as well as for PDPA. And also we did this interferometric particle imaging, IPI as we call it, by just twisting around with the measurements. There are more twisting that people have done. They can combine, mismatch the measurement, mix match the measurements, and then try to see they can get more information out of it. But the PDPA lectures actually ends over here. We will try to see if a lab demonstration is possible, and we can look into the instrumentation side of things a little more. Thank you so much.